Welcome to CoolCAD Electronics here at PCIM in Nuremberg, Germany. I'm delighted to be joined by Akin, Akturk, that's right, and Tom Bianchi. So, gentlemen, welcome to the show. I'm glad to speak to you today. You're specialists in Silicon Carbide, basically. And
yes, Silicon Carbide electronics.
Yes. So for the benefit of our viewers that are not familiar with you, give us a quick introduction to the company and what you do.
So CoolCAD is a growing company based on the East Coast in Maryland. We've been working on Silicon Carbide for almost 25 years. We are one of the pioneering people, like initially worked with the US Army Research Lab to help perfect Silicon Carbide power devices. And later we founded the company and started with software, then over time switched to hardware. We use Silicon Carbide to make power devices for standard custom applications, and also it is for high temperature applications.
Yep.
And the third area is like to use them as radiation tolerant devices. So we do achieve that by improving the tolerance by hard process and also design. And the third area where we use Silicon Carbide is like for high temperature and like the optical applications, like electro-optical designs for UV sensing.
Right, okay. So, Tom, if I can bring you in here, just come in a little bit closer, gentlemen, so we're a little bit, there we go. So, you've been in the advanced packaging business for a long time. You've got a long heritage, as you told me before we started shooting. What are so where are the real benefits you see for Silicon Carbide? Akin talked about the temperature excursions. What sort of tolerances are we looking at?
Yeah, so one of the things that we're looking at different applications is we're trying to see how we can improve the performance of the material itself in its application. So one of the things we're working on is a higher temperature mold compound. So we can go from like a 170 degree, which is your traditional mold compounds, up to 250.
Right.
That's one area. And then the other area we're looking at is using sintering as the die-attach mode, which will help the thermal performance of the package and the component.
Yeah, so this mold that you're talking about is not your traditional metal-based mold. This is something that's more a composite material.
Yes, it's something that would be replacing your existing transfer mold. But the good thing about it is you don't have to change your mold, you don't have to change your temperatures, your process. You can use the existing equipment and the existing transfer mold. So it's just a material change. But it opens up a lot of opportunity for the customers, because now the device can withstand the 225 or 250 range.
Got it. Okay. And the other bit you touched on there was, of course, the sintering. Sintering's become very popular. It's continuing to grow, but at the moment it's mostly based on silver-based materials. And this is an area that you're moving into, or you're...
Yeah, we see that as an opportunity to be able to enhance the thermal performance of the part. So even though silicon carbide is noted for the heat or higher temperature applications, this will be able to get the actual device to be able to dissipate more heat.
Right. Yeah. Okay. So Akin, one of the more exciting areas that you're involved in is working on the space side, and in particular some of the radiation issues that you can kind of run into with these systems. Can you talk to us a bit about that?
I think we're pioneering in that area because most of all the commercial silicon carbide parts are very susceptible to space radiation. So we've been working with NASA and other US government agencies to improve that performance for that. We design spatial devices and we harden them by process and also different layouts so that they can withstand low and near Earth orbits and even further.
Right.
So there are multiple types of radiation that you're exposed to when you're in space, and we harden against all of them.
Right.
Especially the heavy ion hardness is the most critical one that people know that silicon carbide devices are susceptible to.
And it's interesting that the way that you approach most of this is really through enhancing the design. Design is really the key here.
Yes, because it's always been the bottleneck that this silicon carbide device cannot withstand space, so the space equipment cannot go very high powers. Right now they have to stack low voltage parts to achieve high voltages, and it's not very efficient. It also decreases the reliability of the overall system. So they want to use one high voltage part where everything is simplified and the reliability is increased.
Yeah. Okay.
Yeah, I just wanted to add that we're in the process right now of developing a silicon carbide line that handles, that's specifically designed, and of course we'll also do some of the processing changes necessary in the fab, at the fab level, to be able to come out with a product line that is, I say rad hard, but Akin corrects me, says rad tolerant, radiation tolerant.
Okay.
So that's the proper area that we're looking to take care of. But this will be specifically for that application. Yes.
Yeah. This is to enable like next generation of Hall thrusters and power units for like lunar exploration or even further.
Yeah. Well, it's a very exciting area to be working in, and certainly Silicon Carbide's one of the hot areas at the moment. So congratulations, gentlemen, and I wish you every success with it. Thank you for talking to us today.
Thank you for your time.
Thank you.
Okay.
Appreciate it very much.
Thank you.